all about. So this is the outline of today's content. So first is just I give some introduction about ventilations and its importance, and followed by that ventilation application, like what are the things we can do using fluid line and different boundary inputs. Later, I will show some ventilation validation cases and different case studies, real case studies. And last, like not last, like I will spend some considerable amount of time in setting one ventilation real case and smoke provocations for that particular case via Ventil software. So as we know, like ventilations, like the process of replacing air in space to maintain air indoor air quality. So it helps, it has many effects, many aspects. So it's like someone remove unpleasant smell, provides fresh oxygen, prevents stagnant air, so and so. So in ventilation, we have two types of ventilations, like a natural, without any mechanical systems, we achieve ventilation, like change in replacing airs by proper providing windows and doors and other things. So another thing is like forced ventilation. It's like a process of supplying, removing with the help of some mechanical systems like blowers, uh, etc. So in Fluidend, we'll have the provisions to solve like natural forced convection. Also, we can able to like a heating and heat removal process. Also, we can whatever in the ventilation process we can numerically able to solve. And we can for comfort point of view like how much temperatures based upon heat generation, how that temperature transport, everything we can able to model with the humidity predictions. Also the air quality monitoring, like we can model the variation, like for example some like gases which is emitting from something, and then later how it is diluting other things can also able to simulate. In addition, we have particle matter point of view, aerosols or aerosols transport also we can do. Not this is like a not a Lagrangian particle, like this is like in fluid solver itself. We will have aerosol model. We'll solve as a different passive scalars, and that interaction with the walls and the settlings will have some separate models for that. In addition, like a pathogen transmissions, that also we can uh, simulate. Or next is smokes. Like smoke is particularly for from the fire, or it can be from emitted from some particular source. Same thing as a toxic gas dispersion also we can do, even in like a indoor exposed to ambient condition, or it's a fully closed, fully open. All conditions this can be simulated. The scenario can be simulated. Another thing is like from dispersion, like a leakage and further that leads to fire explosion. That is also possible softwares. So major whenever we come to ventilations, the input conditions for the problem definition, that is very important. So user, we have like normally we give boundary condition in the boundaries. So apart from boundaries, we have special like element source information we can provide in the domain also, like as a point or as a group of cells or as a phase. So many options we have. No need to user point of view, no need to model that as a boundary. Even as a point also we can introduce whatever we require. So as a main thing, if you see in ventilation points, in the boundary conditions are like blowers, like we can AC inlets, air extractors, heat generators, heat extractors, fans, leakage definitions, source emissions. These are the major things. So this as user, it will take as the input, like what is the specified. Suppose a blower means it will ask for the particular velocity and temperatures. So AC also the same, like velocity and temperature takes. Extract means discharge rate, it will ask. Based upon that, it extract airs from the particular fluid domain. Heat and generators, if you see, like we can define our region, which is some particular rate the heat will be keep on emitting in that computation domain. Then again, heat extractors also there. We can sink. Basically, it's a source. It's opposite of that. So it can do that. Fans. If you see fans, like there is no additional mass generation adding. It's like a only momentum source kind of information will be through boundary. Leakage definitions, like leakage can be a point, or it can be a surface, or it can be volume. All inputs can be fed through GO. And source emissions, some rate of emission we can specify in some particular region. So as you see this, like we are solving for basic Navier-Stokes equations, solving pressure, temperature, and compositions. First, we'll see few validation cases. Sorry, first we'll see some like ventilation. It's like a partially confined domain. So we have some, for example, this is arbitrary created domain. So I will explain while doing our hands-on training these provisions and all. This is only flow point of view. We have inlets like a extra sorry uh, extractors. Get the extractors. Sorry. So this case, if suppose if you see these two cases, two cases are different way. This is like a artery shaped building. It's like a multi-domain, like we can see. So this particular case, once there is a steady state, basically ventilation point of view will be important in steady state results. So once this is a steady state, how the velocity distribution across these two domains. This particular section we have plotted the velocity vectors. So once we have the ventilation results, we can able to capture velocities or temperature or concentration anywhere in the locations. So even we can see the dead zones, like a dead zone region also we can identify from here. Study. I'll show few ventilation validation cases. This is one particular forced convection. So within, like, we are specifying some inlet velocity conditions at here, like that is the thing. So width, length is around 9 meters, height is 3 meters. This is the exhaust. It will, the fluid enters from the top and it leaves the exhaust. So this case we have measured the velocities, u direction velocity along the height, some particular height at x equal to 6 meter. We have measured how the velocity distribution is. We have compared the numerical result with the experiments. Also, at distance at x equal to 0 plane. So there also we have measured the u velocity variation under the. So this is forced convection. Basically, we are supplying air forcibly with respect to time. It's like that's a particular velocity. Now, if you go a mixed convection, in this case, the velocity also the input domain is different. There we have some temperature difference. Basically, when we have temperature difference, like due to buoyancy, some natural convection will happen. So that's why we have a mixed convection, forced and mixed combinations. There we have measured velocity, also the temperatures, like how the temperature variation with respect to the particular location along the height, how the temperature varies and compared with the experiment results. This is a literature what we have given. This is like one of studies which was performed by some intern from IIT Madras. They had some experiment measurement in some particular labs, like in the ventilation. So she used Ventil software, and she was compared the results. Like for example, in these particular cases, they have some trace 1, trace 2, trace 3, and the particular locations, the measured velocity, and model predicted velocity. Also, the same case, the another lab which have the same measurement versus model predicted velocity are compared. Basically, these for two labs. How the velocity, basically, this case is particularly measured only the velocities. So next is apart from flow, like we can have like some leakage or some emission from some other medium, we can also feed. So based upon that, we can calculate velocities, temperatures inside anywhere in the room. So in addition with that, we can able to see how the concentration, how this is transported via the computation domain. So usually if you see a leakage point of view, not only leakage, suppose if you have some mass which is gas which is entering with high temperature, then that energy also we can able to specify like a rate, or as a mass flow rate, we can specify some particular times like start time, end time, with the certain temperatures. So it will emit in the particular uh, defined directions. So later, as a computation point of view, according to the ventilation, how this species which is transported, that we can able to see. Also the energy, whatever the source time, suppose the source time is the energy, we can see how the temperature transported, the high temperature transported, or is it settling, like as a ventilation point of view, it's going and settling in some particular region, or it is taken away by the ventilation. So that and all we can able to make sure things. This is one demo case, like suppose if you have leakage can be a denser material. So if you have denser material, once if you have solution is there, we can see this settles on the ground. We can see this uh, type of solution for the particular leakage variable. Same thing if it is a lighter. So lighter means due to the buoyancy, like it will higher and like dense, lighter will displace above the ground level. So that type of results we can able to see. This is one of the validation cases which we are interested to see the concentration with the different along this direction. So basically this leakage is from higher pressure cylinder, higher pressure compressed cylinder, the leakage is happening. So this particular case, we measured like how along different length, along radial length, the experiment reported the values. So the same thing we have simulated and we have compared with our numerical results. Later, this was taken to do explosion, and we performed some explosion. Okay, we performed some explosion and compare the ore pressures in different locations. These L1, L3, L3, L2, what they have mentioned over here. Anyway, here we are not showing that. Related to HVAC, some one case which we did for validation was this particular case we have the ventilation rate as this much meter cube per second as the input. Apart from that, some human source also we have considered, and the heat generation. Lamps, like so say some this much watts it is lamp is emitting. In addition, like particles, some particles also we have injected. They basically this is a passive scalar, what they means. So these are the trace locations where we are interested in different variables. So for example, this one particular, it's a temperature variation along the height. So this is like a steady state results. So one particular time we have measured along the height, that particular point, and compared the numerical results with the experiments. Similarly, the same thing, the velocity variations with the respective paper. So now we'll move to the case studies, ventilation case, real case studies, what we did for some different clients. So the first is like a natural ventilation related case. Basically, this is the geometry. The geometry, like outer was removed, like hidden and shown that in internal parts. This case was inside a lot of heating elements are there. Basically, here the heating elements are considered only a convective load. So as a ventilation point of view, I forgot to tell, like we can specify the boundaries as a isothermal, some particular temperatures, or we can specify as a heat flux. That heat flux can be a constant or variable, depends upon users inputs we can specify. This case it's a constant heat flux which is emitting from different surfaces. It's like a like it's a domain which inside different equipments has its own heat generation. So our interest is once it reaches the steady state, how the temperature distribution inside, is it goes beyond some particular limit as a comfort point of view, or how the temperature distribution was. That was the interest in this particular study. You can see it's a complete mesh. So this is the complete isometric view of mesh. So inside it a tetra mesh, and outside we can see mesh. So so this is the distribution of mesh. I will show the results. So in this case, we didn't consider any radiation, so only a convective the heat load, and just we have solve for the Navier-Stokes equations coupled with the pressure and also energy equations with the turbulence model. So these are some cut sections at different velocity contours we have made for different sections, and we are showing the domain how the velocity distribution is. So we can see because of heating, the air entrained from the side inlets and it is escaping to outlets. Another important thing while doing the natural ventilations, the conditions are very important. Even morning also I was telling. So suppose to get the full good convergence in natural ventilation case, the proper condition should be very important. For these cases, like we'll specify like outflow, it's like some particular static pressure will specify, but in inflow there will have some different boundary conditions. There it will calculate the static pressure and it will force in the inlets. So that step of boundary conditions, it will make stable results. We'll get steady results. Particularly in natural ventilation. Forced ventilation, it's not a matter, so we can get to convergence very fast. But natural ventilations, that's a very important to specify the boundaries in our outlet open conditions, very important. So in the same section, we have shown that the vectors, how the flow profile, velocity profile. So this is for temperatures. As we know, the heated air you should always due to buoyancy, then higher temperature settles on the top. Based on that extractors information, finally the distribution depends upon the extraction rate. So have a result shown for different sections. Now we'll move to next real case. It's like this case, this case, both cases are almost similar. Similar means as a problem definition point of view, it's similar, but geometry is different. So in this case, not only convection heat flux, the radiation heat flux also as a input through different surfaces. Based upon surface, the different values comes. So interest is like, so what is the maximum temperature we can see in the due to this some particular atmospheric condition. So we are not forcing any velocity. So basically, based upon heat load and outlet conditions, opening conditions, it extracts its flow entrains from the bottom and it escapes through the top. So that was the enter. So here, whatever the first two are geometries, different views, and the same thing is the mesh. So even this case to capture the entrainment effect. So all sides are extended, the mesh are extended all sides, but whatever the mesh shows only the inside domain. So this is the gas temperature once at the steady state, how that gas temperatures, we have plotted different sections like two horizontal and vertical sections. We have plotted the results for the gas temperature. This is the radiation heat flux along that heat generated region. You can see more in the heat specified region, and it was transported in other region. Other than that, this is like a speed, like suppose if you have temperature potential difference, so automatically due to buoyancy, you can see a force towards that side that will be a contribution to the momentum equations, which will generate a flow in that particular directions. So this is a flow resultant speed. So we'll show other few more cases we are as a ventilation point of view. So in this case, it's like a hospital environment. Like we have bed in different rooms. So it's like a ventilation. These are ventilation results. We have some like a inlets which is providing fresh air. And in this particular ventilation conditions, like suppose some pathogens like emission, it happens. So how this is spreads with respect to time. That was the study which isn't. So with respect to time, we can see like one particular time there's a chance of going inside that room also. Another case is also it's like a pathogen kind of thing. So in the ventilated room conditions, suppose if you have some. So this animation shows how the pathogen spread in the ventilated room. Basically, we'll solve simultaneously, like not pathogen spread. So while solving this momentum, this Navier-Stokes equations, we'll simultaneously solve this pathogen transport equation also, so that we can able to see with respect to time how that spreads in the computation domain. Even in this case, we can see the mesh structure, like a nutshell view. So domain. So we'll move to next case. This one of the mall study. So basically the interest is to study the smoke. Suppose if it is generator smoke, is it possible like this, suppose fire comes, they will activate these fire extractors. So they want to make sure that this particular time, is it possible to evacuate all those whatever fire that smoke, whatever generated. That was the intent. So we have shown only few results. This is also like a fire extract, like a smoke extractor to test the effectiveness of extractors for the smoke. So it's a fire curve, like some particular time the fire will be there, then one particular time that will be deactivated. So later these extractors started extracting air from the top so that we can see one particular time all the smoke got extracted. It's got escaped through that top vents. The forced. Basically, we can say it's like a forced function. So this is like on smoke propagation. So in the ventilated conditions, suppose if something fire or something happens, how it spreads, and later once it's got extinguished or fire extinguished, how much time it will take to evacuate this smoke. That was the main interest in this particular study. Few more like some consultant studies flowing around the market area, like suppose the wind is there, so how the velocity distribution it will become. Basically this case the atmospheric wind velocity also considered, so how the velocity distribution, that was the main interest. So the mesh whatever we created based on the undulations, the undulation effect also considered in this mesh. So this is like a fan effect, like some vehicles, like suppose if you have some fan, how how the velocity profiles inside that region. That was the main interest. It shows that the mesh and mesh structure and other things. It's like a natural gas leakage in an apartment. Suppose some leakage happens, how it spreads based upon that connectivity between these rooms. So basically, these cases are at a different ventilation rates, how this spreads. So this shows that mesh structure, typical mesh structures, the surface mesh which I have shown as a mesh, shown as a surface mesh. So it's like a hospital ventilation. Suppose it is like a outdoor and like a partially confined domain. So if we have some wind velocity, like how the velocity distribution, like how velocities or what we are. So it's in confined room. So previously it's a partially confined room. It's a ventilation confined room. So there we have So we have plotted that flammable fuels also here. This is another case which was interested in ventilation. So here, we have plotted the velocity streamlines also based upon that ventilation condition, how the streamlines look. That also I have plotted. It's like hydrogen leak in a laboratory. So ventilation come leakage study. So this is air quality inside a river tunnel. Suppose some emission, like something which is emitted. So how it is dispersed in that tunnel. That is the main interest. So this is like a dispersion high-speed train station. Velocity distributions. So this is another ventilation case which will deal with the underground train stations. Basically, we did this simulation did with the moving fish concept. So also here we have did some pollutants. Suppose how the pollution transported during this movement, train movement in the past. This is another case in plane fire in a train compartment. Suppose it's happened something in a particular location, how the smoke spreads or temperature spreads. That's so this is like a ventilation in that some leakage of the cloud, like a this is some ventilation study in the ventilation and order study in that waste treatment plant. Again, ventilation study in that foundry. We have measurement for CO and other things also. This is like one indoor particle dispersion case. Suppose by for something, if some parcels comes, based on ventilation, how it will, with respect to time, it will move inside this case. So basically, this case will be taken as a for hands-on training. I will explain it. So now we'll see how the particles are transported in the ventilator. Oh. So once the particles come, higher particles get settled in the ground. So the smaller particles, it will transported along the flow. So based upon that wall attached conditions or other phenomena, the particles will, like some particles may escape through like doors. Basically, here we can see some particles coming out. Based upon the ventilation directions, this will be transferred. This is another case which we have the multi-floor case. Like suppose some fire comes, like a fire curve. Basically, this case like a fire curve. So they have specified some rate. Basically, this is a fire curve. So initially, some 0 to 30 seconds, the ventilation, like it's a transient ventilation, will build up. Then one particular time, fire stops and reach the maximum. Then it goes to 0. So how much time it will take to evacuation? That was the main interest. It shows some temperature variations along with respect to time and smoke products during evacuation process, how it will be. So as a part of this case is as a part of hands-on training. So I will show you more details about this case. So this is one of like a ventilation come fire case. So this case, if you see, like it's a ground floor, doors are kept open, like in first floor, second floor. This is dome. So these are like working places in the second floor. And if you see here, no, also like supply air grills, and size also have given like typical size is 12.6 meter height. a return air will, supply and diffusion. All these things are we have introduced as source information. In addition, this is the main entrance. As I told, it was open, kept open. And based on this condition, first we have simulated the ventilation. Before that, this is some more information where the fire source is. Basically, if you see, this is the fire source. So this also one particular time it was got extinguished, like it will be fairly stopped. Later, how the flame propagates in that ventilated condition, that was the interest. So here we have shown the mesh also. Basically, in this case, we set up like through Ventil software. Maybe I will show you how to do this. This is a number of elements, nodes. Elements type is tetra. So near to fire source. Basically, in Ventil, like it will refine mesh. I will tell you, like it's a built-in mesh. It can generate based upon the obstacles, definitions, and all. It will refine the mesh its own. These are boundary, initial and boundary conditions. How much air is supplied to what rate, total air rate, and direction. Direction is also the conditions, wall conditions, isothermal wall condition maintained, and atmospheric pressure condition. Also, that the fire source characteristics, like this the way it was, the fire was started burning. One particular time it was suppressed. So the numerical aspects, like we have flow is turbulent model came down, gravity model was activated because of this high temperature. So numerical schemes we have used in UVS. Its type is transient compressible flow, pressure coupling. So simplex is used. Solver is NSCT. This is the ventilation results. So some particular sections like how the velocity distribution is. So that was the air information which is fed to the inlets. So we can see this is the velocity distribution of the inlets. So same thing in the different planes in the 3D view, we can presenting the results. So next is the temperature. So this particular section shows how the temperature distribution is due to this ventilation condition, how much comfort point of view can make sure thing. This is in 3D view, isometric view, like different cut sections they are shown and presented the temperature distributions. So in these conditions, like the flame was, the fire was activated as a fire cut. So this is the smoke propagation. Basically, this is the CO, like the range, maximum range was 35 ppm. So for 1 minute later, this is the distribution of smoke propagation. Like we can see 2 minutes, after 2 minutes, 3 minutes, 5 minutes, 10 minutes by the time fire got extinguished. So later we have the provision for the visibility also. Like if you see higher values 30 meter, we can able to see in these regions we can able to see 30 meter, but in these regions we can see only a little range. We can show almost close to that it will be 0. Later, how this visibility affect on the top can able to see. This is 3 minutes. This is 5 minutes, 10 minutes, 20 minutes. Same thing the temperatures, like with respect to time, how temperatures go. This is on an animation for the iso surface of the smoke. So the concentration we have set for 10 ppm. So we can see one particular time it was accumulated on the top ceiling on the dome part. Later, due to this fire extraction mechanisms, so we can see almost particular time like around 1,000 seconds, like almost all got extracted. So it tells like how much time it takes, and immediately we can able to simulate and see. The only thing now we should know the fire condition, and when we are extinguishing that and all, so we have to make sure. So once that is there, we can able to simulate this type of cases. Now we'll go for hands-on training. So I will same case I will load it. So for example, uh, basically I'm doing hands-on training in the Ventil software. Ventil has many modules like Ventlim. Basically, this is the family. Ventlim is a family from Ventil. Ventlim is particularly for ventilation purpose. So now I am this case already we have created the geometry. Just I am showing like the geometry import. First I will open the geometry. So as a procedure point of view, as a ventilation and flame propagation, smoke propagation, I will show this case. Later I will explore more options like to do, like how to do it, and I will explore. So in this case, this is the geometry which created through C venting. So here we can see this is like a lift. Basically, as a flow point of view, we are assume that it's a closed, so it's like obstacle. So another thing is these are all our obstacles like a reception kind of setup. So the doors. Here we can see or whatever the defined components. Basically, this method, like here there is no need of this is like a built-in 3D domains. There we can drag and drop over there. Drag and drop procedures. Like we have cuboid domain, orbital domain also we can able to make. Walls we can introduce, openings we can introduce, occupants we can introduce occupants, whatever we want. Then sources we can introduce AC heaters, extractors. Again, leakage point of view, it can be a species, or species can be a point, area, or volume, or it can be as a heat source, and also possible through point, area, or volume source. So apart from that, the boundaries, like the boundaries, what are the other boundary condition, ACs, heaters, extractors, so many options are there. Also, we have studied this case, the ventilation, we can able to simulate a CHT case, like basically the flow interact with the thermal. Also, it's possible in this ventilation software. So now if you see, we can see, when if you click, you can see what are the things are there in this case. These are domain. So this has the external walls. In these external walls, we have introduced the door. Similarly, this is the external one, other external one, we have introduced door. Suppose if you want more door also, we can drag, say for suppose we want one more drag over here, door over here. Then it will ask what is the shape, rectangle. So we can specify the location, or otherwise we can simply okay. Then so we can place wherever you want, like a left click to confirm the points, right click to confirm. So this open is a hand image. Similarly, we can do the modifications, whatever we need. The same thing, basically, these are multi-room. We have defined as a multi-room. So some particular cases, if you want to define wall or we want to open that, and also it will show as an interface between these two things. We can define conditions based upon our problem definition. It can be a blockage, or it can be a partial blockage, or it can be a we can open also. We can set phase porosity equal to 0. Basically, these are phases which can give different conditions based upon user's input. So other than that, it's a fire definitions, like a fire if you define. Basically, in this spindle, all problem definitions will be taken through geometry level. So for example, leakage. It will take point source or whatever may be volume source or surface source, that doesn't matter. If you introduce, automatically these boundary conditions will, once we load this geometry in GUI, automatically identifies this. Okay, this category belongs to extractor. So as a user point of view, you have to specify only the flow rate, extraction rate. So only as a user point of view, they have to provide only the. Hello.
Chandra sir,
yes.
can I have a moment? Actually,
Yeah.
you're changing the slides. Actually, I think this slides are stuck. We can see this ISO surface animation.
Okay. Oh, actually I have to share that.
I think you are sharing the
Oh,
PowerPoint,
PPT.
not
Okay.
the.
Okay.
Yeah.
Okay. Sorry. Thanks to reminding. So I will otherwise I will do one thing. I will close it because.
Yes, sir. Thank you, sir. Thank you, sir.
So what I do is I will. Is it visible? Hello.
Yes, sir. Yes, sir.
Okay.
Visible, sir.
Okay.
Yes.
So whatever the same case I have shown, I am showing in that Ventil platform. So basically, this case setup we created Ventil. So just I am loading that geometry file and showing how things are defined and other thing. Okay, no? So this is the domain. So basically, if you see in Ventil point of view, the geometry takes that problem definition itself. So for example, is that the tree what I was explaining. So we can able to make cuboid domain. Basically, it's like a 3D domain we have to define. It's not like a from point or anything. But only thing we have limitations, like we cannot go for curved, very curved things. Or through arbitrary options we can go, but that also as a like a limitation we have. Suppose if you have design point of view, have very complicated geometry, we cannot make use of Wendell. So we have to go for multi-physics that has many facilities. This is like a like even who don't have knowledge also they can able to simulate using the Ventil. Ventil means Ventlim is a part of Ventil as particularly for ventilation purpose. Similarly, we for Ventil family we have a few more like Ventex, particularly for explosion modeling. Explosion means everything whatever morning I have explained, like gas or solid detonation or particles or all other functions are there. Then other than that, when fire, reserved for fire related studies. So if you see a geometry point of view, the pattern is same for all Ventil families. Only based upon Ventil film or Ventex or Venpair, that only the source or that additional things will be added or removed. That's a important change we can see in the whole Ventil platform. So when clean point of view, the ventilation, all informations will be available. For example, we have two options like a cuboid domain, arbitrary domain. Arbitrary domain means we can simply keep on dragging and we can put our points. So that finally you have to specify the height, we can able to get arbitrary domain. Cuboid domain means we can go with the different multiple. For example, this case is like a multiple domains we have kept. So the interface we have to specify whether it's a closed or open. That we'll see here. Other than that, we can place partition walls inside the buildings, and blast walls means suppose CHT point of view comes, these will be the structures. These are openings. Suppose if you want to introduce openings, you can see this case, these are domain. Uh, these are the doors. These are called openings. It can be a window or door or vent hole. So vent hole means some particular. Suppose if you define door or window, will show only the option as open conditions. Suppose if you define as a vent hole in GUI, it shows open condition for two. We have provisions. It can, if you want to close, also we can close. Otherwise, we can open. So that's the main difference in the openings. Apart from that, occupants we can see, we can define humans, tables, chair, machines, boiler, pillars, beam, general occupants, structure occupants as a CHT point of view. Whenever you introduce blast wall in the wall or occupants inside that domain, this will be separately meshed. Basically, while meshing, it will basically, as I told, it's like an automatic mesh generator. So that identify this as another structure, another solver. So it will create a mesh and create a separate measurements for this, and it will create for separate for fluid. Later, it will find the interface for its own. That's another advantage for a. For example, when clean point of view, this is when like a fluid is coupled with the thermal. Same thing if when fire point of view, it will couple with the stress as well as thermal. As Vendex point of view, it couples with stress. That's a FSI case. So based upon application, this fluid is coupled in different way with the structures. So now if you come for ventilation equipments, if you see heat ACs, like we can place inside the domain. So AC heaters, blowers, extractors, we can place inside the domain. No need to be think of boundaries. Without boundary also we was talking. Initially I was telling about the boundary conditions. Other than that, source we have different options like a source. It can be a point, area, volume, or heat also. It can place anywhere we want in any shapes. Uh, Another thing is in the boundaries we can have different conditions. It can be AC or velocity in the boundary condition, blowers or heaters, extractors, everything we can make the help of this. Another thing is the structure boundaries. Whenever we have structure, if you coupled with the structures, we can specify our own boundaries in the define our own boundaries wherever we want. So that's a boundary condition. So we'll see this case in detail. Suppose this already we have defined. So for example, this is the one cuboid domain previously we have defined. So in this domain, suppose if you click over here, it will show all informations like what are the things are there. Suppose if you want additional information, suppose this is the one wall. I want to introduce one like a door or anything. I will do that. So I pull the door. So you drop it over there. Okay. Once you drop it, it will ask what is the shape. We can have our own shape. We have other options also, circular or face cover, whatever maybe. So then it will ask the size. If you specify location, it will place according to this center. Or otherwise, we can go with mouse also. We can place. So mouse, if you move, it will show here like what is that coordinates. If you know exactly where you want to place, that's the best way. So that according to our needs, properly we can place it. So you can see this. So this is that new openings I have introduced. Not only openings, I will show other things also. I am introducing one machines. Machines have to follow something. Suppose we are introducing some anything in the boundary, we have to put over there. Suppose inside the domain sits, we have to make sure. Here we have to drop intention, so we have to follow some three procedures. So spear, cylinder, or whatever we do. Sorry, some work is going on. We can hear some noise. So we can specify the coordinates exactly where we want to place. Otherwise, you can just give OK. Then through mouse we can place. So I'm placing here. Fit. So I introduce obstacles. So once if you load this geometry in GUI, it will ask whether, for example, in this case, it will ask whether it's an open condition, means it will ask the ambient conditions. In this case, it will activate that porosity, like we can give full porosity like 0, or it can be partial also we can provide. So suppose if we give 0, totally the flow cannot pass over this. So it's like a blockage. So I was talking about some subgrid models in this. Suppose in this case, suppose if you activate subgrid models, like in the flow, it will generate some source stamps, and we can able to capture. Suppose I have some flow along this, we can able to capture even the turbulence behaviors, everything in course mesh. So apart from that, these are the structures like what we have. So similarly, we have different domains. Also, suppose whenever we are introducing one domain and second domain, the interface will be considered as an internal phase. So this interface we can specify separate conditions. If you want to open, if you want to, there is no partitions, then we can specify phase porosity equal to 1. Or otherwise we can give specify as a obstacle. Like obstacle means as a there flow cannot enter means we can specify phase porosity equal to 0. Even partial porosity also it accepts. So this is about the geometry. Maybe we will see the case setup, and suppose time permits, I will explore more options in that geometry. So now this is okay. Now already we have the geometry files. So basically these are F3D means these are the two geometry files which are interested in the case setup. Now we'll open Venclim GUI. Oh, sorry, I have to share again, correctly. Can you see my screen now?
Yes, sir.
Okay, fine, thank you. So I'm opening this geometry file. You see a lot of like obstacles and so many things. It takes some time, depends upon machines and number of
So
objects.
meanwhile, can you answer a few questions?
Yes, yes, please.
Yeah, somebody's asking that whether we have to do the transient or static analysis for this one.
Which case? Ventilation case?
Yeah, I think so, sir.
So ventilation case, we can go for steady state. Directly option is there. Suppose sometimes what will happen now, if you have very high sources, for example, heat source or something, no? Like in that cases, like we may have some numerical instability. Then anyway, our interest is like a steady state.
Okay,
So
sir.
we can use higher time step so that we can reach the steady state faster.
Okay, sir. Another one is which would be better boundary condition, heat source or heat flux?
Heat source is not bound heat flux and heat source. Suppose if through wall, if you have suppose if it is a wall, then best is heat flux. That's the best condition. Suppose in inside domain, there is no boundary condition we have defined. We didn't consider any partition over there. Then we can go for heat source as a element based inputs.
Thank you, sir. You can continue, sir.
Okay. Now the case setup is loaded. So now what I will do is already we have defined that case information. So I will load that. So I will. So whatever previously set up informations will be available in simulation.data. So I am loading that information so that whatever things have, it will automatically set over there. Even here setting is not a matter, but still we have many numbers, different extractors and other things. So I am using this. Because of many informations, it is storing the old values, so it takes some time.
Sir, meanwhile, another question.
Yes, yes, sir.
Is it possible to streamline all evaporative coolers of the compass? And if yes, then how to optimize the cooling performance?
Sorry, I didn't get. Can you repeat the question?
Is it possible to streamline all evaporative coolers of the compass? And if yes, then how to optimize the cooling performance? I'll send that question to your chat box, sir.
Okay, okay, I'll see. Streamline means like it's like arranging, or maybe the as a safety tool. One thing I can tell, like this is like a see this placing above coolers or whatever maybe, that's like a these are provisions which you give, but this based on ventilation results, then only we come to know, because I'm not that expert of placing optimized placing. So basically what I'm explaining is the way we can able to define components, and we can that's what's the way to specify the inputs under. Okay, so now we'll
Okay.
move to our
Yes, sir.
case setup. Now this case, see for example, this is a deck. So if you want to specify as it's a multi-domain, because this is a big atrium. So these phases and all we have to set as a phase porosity equal to 1. Then flow should transfer. This case, this is that second floor, that walking path, that should be set as a phase porosity equal to 0. So again, the phases. So this is the way whenever we have come over there, we have to specify this. In addition, suppose the vent hole. So there also we have to specify this is the opening. Suppose if this is the door, so we have to specify that as the phase porosity equal to 1, because this is the open condition. As per this is as per problem definition only, where we want to close, where it to open, want to open. That's user's thing. So this case is concerned, this door is kept open. So apart from that's the domain. So we can specify the initial condition. Basically in the ventil, if you see this tree, is to specify initial condition as well as the boundary conditions. So as per this internal phase, these are boundaries. Also, suppose if you select the domains, so this is the region, so it will ask for the initial condition. Suppose if you want to add some scalars or something, we can add from here. Suppose if you want to simulate some dispersion, anyway this case is concerned already we have added, because we loaded that data, it automatically takes to whatever the things is required for this case. This case here as a carrier, smoke and all shoot HCN. These are the products which is generated during this fire. So I will tell you how we are defining these things. So in addition, if wall comes, it will ask for conditions like is it a closed, if it is a closed, or it can be open, or NRB is also there. In addition, we'll have other condition. Wall type can be no slip, free slip, lock slip. Wall conditions, other wall conditions are isothermal, adiabatic, heat flux, radiative, convective, 1D wall. These are the other options we have in this. Apart from that, suppose we select isothermal, like we have to specify the emissivity also. It will be used, suppose if you are solving for the radiation and other things. If you see wall, other than that, sources, we'll see one by one sources. So basically this is emitting speeds. So if sources comes, it will ask what is the flow rate, what is the velocities and directions, and starting time, end time. These are the source informations. Doors already I told, like doors if you specify that defaults it will kept as open. So all our species source. Extractors, when you see the extractors, it will ask for that flow rate. So that's why I told, like whenever we define the geometry, we are defining our problem definition itself in the geometry. So here it's only, it will ask that informations like magnitude. So door we have set, so it is set as ambient, it is exposed to ambient, so it will ask ambient pressure and temperatures. So now these are all, let it go. We'll see that fire source, that's important things, this case setup. So this is the fire. Whenever we have fire source, it will ask for how much is that. This is input is in megawatt. So convective. This first is convective, radiative, start time, end time. Basically, it will do like a initially it will start from something. It will peak some particular time. It will later it will based upon this peak end time, it will be constant, then it will go to 0. This is the default trend we have for Firecurve. So apart from these things, only the boundary condition, initial condition, and this species definition. Suppose if you have some leakage, then we have to define our own species through this chemical action. So next, this case setup point of view, we have to go this way. Simulation options. We can select physical models like laminar also we can go, but this Wendell we have limited our turbulence model. One is for laminar case, another is K epsilon, another is SSTK K omega for wall bounded thing. So in this case, K epsilon is activated. Other than that, like buoyancy, like because gravity models we have activated, that's a buoyancy. So once if we activate buoyancy, we have to specify the gravity direction and reference density. So you can see the explosion fire, but that was hidden because this particular model for Vendex, that will be hidden in Venclay. Same thing in fire, these fire related things that will be hidden. So totally reaction rate and all, it is totally chemical reaction definitions and all totally hidden. But here in Venclay we have other things like a radioactive decay model, like we can this decay of this components, decay components we can make sure. Also there we have option for solving the aerosol modeling, and aerosol and radioactive material coupling, that comes like a radio decay material be carried by aerosol, that's be called as a radionuclides, like aerosol and radionuclide or get interaction, and how much aerosol taking the radioactive material and other studies. Other than that, like we have the particles model, as I was telling, that Lagrangian model. Anyway, for this case, this is not required. So this case, the important thing is we are selected the turbulence model and buoyancy. I will go for this setup. So this and all we are not doing, just apply. So mesh. So mesh means we can see like we have the provisions defaults we have for unstructured, and we have provision for structured mesh also. This case unstructured mesh. Basically, this case is multi-box. We have to select the bounding box method. Also, the grid refineness. Basically, this as I told, it's an automatic mesh generator. So only thing we have to give some non-dimensional parameters to make sure to improve our mesh. Suppose if it is very fine, we can reduce the grid fineness. These are overall factors. It will reduce the mesh. And it's other control, like in XY direction, we have we can control. Or if you want in Z direction, only mesh control in Z direction we can go. Or otherwise, this minimum maximum, it's like a stretching. Suppose if you want to verify in one particular like Z equal to 0, if you want goes towards other side, we can tune these parameters. This case already, this case setup belongs to this mesh. We are not disturbing anything. Next is solver. So this case, first we are doing the ventilation. So we are doing as a steady state. So, or suppose while doing this transient leakage, like for example, spire, we can switch to transient. So usually it's a steady state. So their time step doesn't have maximum, doesn't have the role. So only how much cycle we have to simulate. Other than that, the solver point of view, no need to change because these are default parameters. User point of view, no need to change anything. Suppose if they want some solution is not stable or something, then they can change. Unless otherwise, then no need. Then thing is, we can introduce points also, trace points. Suppose we want to measure some quantity, it can be a velocity or whatever. We introduce some points. Built in, it will dump some files, which will be result will be stored in the trace locations. It may be pressure or whatever variables we are solving. So other than that, how much frequency you want to save, say, results and other information, trace information, restart, save. These are the other information. So now according to this is the setup we need, case setup. So once all setup is done, then we can generate the case file. So before generating case file, we have to give the case location where we want to dump this case information. So once set the information, then we can go for creating case files. Basically, whenever we click these options, so what it does is it will according to the obstacle information order, it will collect the important places we want to define the mesh, so that later it can create a group and define conditions over there. Other than that, based upon these points, it will create the mesh, and it will group it based upon these definitions and assign conditions. Final all assigned conditions, this will be written in INP file as a file format for solver. So it will write in the particular location whatever we gave. So as a user point of view, we have defined geometry information as a, in geometry itself, we have defined the case informations. So here we have given the magnitudes, whatever respect to our ventilation conditions. Finally, we are generating the case file. Just I'm generating, we'll see. So based upon this, once this generated, mesh generated, it will display the mesh over the geometry. Suppose if you want to increase based upon, if you do few cases and grid independent studies, we come to know like what is the typical mesh we have to use. Suppose if you don't know, you can use the default mesh. From there, suppose if you want to refine it or coarsen it, depends upon your need, the grid fineness and other factors can be changed. Now this is like a file again, if this speed for generating mesh and case depends upon number of domain size and the components and the parameters. So this case, like a bounding box method we have chosen. So it will be, first it will mesh based upon the outer boundary information. Later, this region it will remove. So now first I had meshed, then you can see what sort of the process is happening. You can see my screen, right? Hello?
Yes, sir.
Okay, fine. Okay. So here we can see totally meshed throughout these bounding boss options. So after that, it has splitted like 5,42,746 fluid elements and saving in the neutral file. So not only it write the mesh, it will dump all information, the case information also, whatever we defined. So now it's writing element data. So while writing case files itself, it will write that node data, element data, and group informations. Everything it will write. I will tell you. I will show you what are the information right. So this case as a ventilation point of view, even suppose the same geometry we want to do some dispersion or explosion, we can make use of it. Like we can define a premixed or whatever may be according to the definition we make. We can same geometry can also use, or even we can use the same mesh also.
Sir, there is one question.
Yes, sir, please.
How solver accommodate the flow of non-Newtonian fluids like smoke here?
So there we have to given these cases we are, that is the material definition, sir. Based upon material definition, it will get the information. So this case ideal gas, it defines ventil default define that as the ideal gas, air, and mixture other things are as ideal gas. So based upon ideal gas assumptions, it will, based upon this mass fraction for individual cases, it will calculate that equation of state. It will calculate the density, like if you see that equal to rho by RT. So this for ideal gas. Suppose if you want to have different material, then we have to define as a material definitions. Now this case is generated. So suppose if you want to see the mesh also, you can able to see. Suppose if you want to change some parameter also, what we have to do is we have to go there, the mesh. You can change if you want to refine further, means we can go for 5 numbers like 4, 5. We can keep on increasing. Suppose if you want to again pose, means you have to reduce. You can go up to 1. So this is up to the user. So once these case files are dumped, it will dump. I will tell you how. So this was at the base geometry file. This is the simulation data which will be used later for reloading the setup. Apart from that, we can see the fluid dot element information, nodal information, group information. This is the INP files. So these are the basic inputs which will solver will read, and it will generate some supportive files later. So no need to worry about that. So if you suppose if you want to see what is the inputs it has given, that what extract, so it will like what solver reads, that's the thing. So here we have been consider as like it will tell how many number of elements, nodes, and all informations are there. So as a rental point of view, no need to do anything in the INP file. So because so this will like
non-node is meaningless.
okay, this is the material definitions, like a mixture. Material when mix is a mixture of air, smoke, CO. So
For the PPT.
Huh? Hello. So this element information is written, element boundary informations, all informations are there. Last it will define that boundaries. So these are the boundary conditions, whatever we defined. So boundary conditions, some wall, this is wall boundary conditions, cell porosities, and these are initial conditions. These are the sources. Suppose we want to do modification also, we can make use of this, and we can solve. Next step is, anyway we are not going to solve. This is the case setup. Suppose if you want options, I will show more options in the CAE. I will explore some more features over here. Suppose if you are do freshly, you have to create one room. So you have to specify that length, width, height, and all. If you want to specify this exactly, or otherwise we can simply paste the center means like a 0 if you want to specify. So this is the room. So arbitrary shape also there. I will show after this. So we can introduce some partition walls. CA means from the ground height, how much is that height? We can place directly, we can give the coordinates, or otherwise we can partition wall. We can introduce doors or whatever. or you have placed in it. Suppose if you want to delete also, you can delete it. Like we can introduce machines or whatever. Maybe. You can modify also. So we'll introduce some. So some extractors will introduce. Suppose if our problem definition is that, then we can case export. Can specify the file name. Now geometry point of view, it's okay. So we have defined. Now next thing is we'll close this. So now first thing, whatever I told, like whenever we want to set up like a domain initial conditions, we'll see like a door, like it's open to atmosphere. We consider ambient pressure and temperature. Other boundaries default it is closed. So the extractors, so you can specify flow rate, apply. So other boundaries default it's okay. So then the partition one, so it's like a blockage or we'll consider it's a blockage. So this porosity, like this also blockage, all are blockage. So now next is that location where you want to save it. So default epsilon. So this case no, like only flow industrial, so no gravity. So nothing is there, just apply. Mesh will use default mesh. We'll see that. Solver steady state. Output we can add some points. So this, wherever you want, you can reduce points. Result save. So other than that, okay. So now our case setup is ready. So we are generating case files. So while generating case files, it will mesh based upon. So now meshing also done. You can see. Suppose we want to refine further. So I will see. I will introduce or I will more refinement only in this direction. I will make it 45. Apply. Close. Now we can see this is the mesh structure. So now we'll see here. You can see it's more refined in this direction. Suppose if you want more refinement, XY, make it 30. So generating mesh means not generating mesh, it dump for the case files also to solver to run. So now it's refined the mesh. So now if you see in that particular case folder, so it's a row. These are the inputs, solver inputs. We'll see the solver inputs. Default it will assign as a air as the material. It's ideal gas. Viscosity, Prandtl number, and everything defined. So this case like a steady state, compressible viscous turbulent fluid is air, K epsilon coefficients, everything we did. So these are the underlying system for this pressure velocities and all informations. Apart from that, the flow rate, this is the extractor condition, pressure outlet, and others are wall. Apart from that, we have one phase that we have defined as a phase porosity condition 0. And porosity, other three are obstacles as porosity, default subcritical activated. So these are the initial conditions. We'll make default conditions and we'll do them. We'll run this case. So this is the way how to run. So one particular time it will dump some results. Suppose in the meantime, if you have anyone questions.
Yes, sir. There is one question. Is flow of smoke is Newtonian 1? That is a question. Whether it is Newtonian or not.
Yes, Newtonian. Like we'll specify the viscosities. So we are not, for these cases, we are not dealing with non-Newtonian, Newtonian.
Okay, sir.
Hello.
Yes.
Raghavendra sir, if you have any questions, you can ask, sir.
Yes, sir. This is my question. How can you treat flow of smoke as a Newtonian fluid, sir?
So just a minute, sir. Arun, sir.
Yes.
Arun, sir.
Yes, yes. Actually, have you got my question, sir?
Yes, yes, I got it. Just I'm asking
Actually, whatever my knowledge is, in CFD, we are solving mass momentum energy along with some state equation.
okay.
That's okay. I will assume that for smoke, you are assuming state equation as ideal gas. But even how can this energy equation and momentum equation, which are generally derived for the Newtonian fluid, can be solved for smoke case in your ventil, whatever you are presenting? Because what
Yeah, hi, this is Aramurthy here. Smoke
Newtonian.
is basically a collection of particles, so it is not non-Newtonian. You have to model them as particles. The particles, depending on the size, they have different behavior. Very small particles will have a lot of Brownian motion controlling them, and large particles will behave like individual particles, which will settle quickly. But if
So
you
are you
try,
solving
if you try, it is not a, using a non-Newtonian fluid, you cannot model that. You have to use a two-phase model for that, or aerosol model, which is also available in Ventlim. Ventlim has a model for aerosol, so you can define the smoke as aerosol and model how it moves, how it disperses. But it is often actually when you are doing a fire related to smoke propagation, then these things are not so important because fire is dominated by very high convection due to the buoyancy. So there the gas assumption is more than sufficient to see where the smoke is going. But for other cases where you have particles in a cool atmosphere, like in a room temperature thing, then you cannot really use a Newtonian description, or you cannot model it like a species. You have to model them as particles and see how they drift.
so? Your ventil is a toolbox in fluid dyne.
Yes.
So, depending upon the material we are specifying, it will take the state equation.
You have to choose the equation because you have to tell what behavior each material has. It comes with its own database already. But apart from that, if you have
So
any new material, you have to define how it behaves.
whatever
But the
simulation.
state equation has nothing to do with this particle thing. For particle thing, you have to use the two-phase model called aerosol model.
So you are solving in Lagrangian frame of reference or Eulerian frame of reference?
Both are available. For large particles, you can use Lagrangian framework. For the very small particles, you can still use Eulerian framework, but you are going to solve a separate set of equations for those small particles. I think in one of the talk that is scheduled tomorrow, I think he is going to give details of how it is done. So we solve actually separate set of equations for the dispersed phase, and it will have components for Brownian motion, effects of gravity settling,
Nee,
then
little bit
particle
actually I
filters and
want
other
to
things.
confirm.
Yeah.
So this ventil, what actually you want to simulate means through the smoke simulation, what is our objective when we are just simulating it for a big mall or a big building? So
Yeah,
what is the basic objective of this your ventil?
the objective is basically when you have a fire, actually you need to see where the smoke goes, and you need to make sure that it is ventilated properly, or it doesn't go into the places where people are there. It also is used actually as a first step before you can evolve an evacuation plan.
So how actually we are deciding this?
Depends on your application, sir. Depends on what you are trying to do.
In post
Depends on what you are trying
processing,
to simulate.
actually when you are having some toolbox, obviously you are going to have some specific purpose. Now you are, as you
Yeah,
have said,
vent is for that. Vent is actually not meant for fire. Strictly speaking, the vent is mainly meant for ventilation. Whereas vent fire is meant for fire and smoke propagation. There you can use other models. But those models are available in Ventclam also. So it depends on what kind of fire you are simulating, what kind of smoke you are trying to simulate. If it is a smoke generated by a fire, actually, as I told you, it is a highly buoyancy driven flow. The gaseous assumption is more than sufficient for this. Whereas if the particles are coming or smoke is coming from some other source, then it's a different thing. Then you cannot really use this method.
okay, but what I feel ki it's a, it seems from my consideration, it's a modeling pitfall because you are simulating smoke by Newtonian fluid. It's I don't think it's a good thing.
I see. Mhm.
I accept my knowledge is not that much thorough, but I don't
See,
agree. Okay, sir. Okay,
see,
thank
this
you.
smoke. Okay, maybe we can discuss this separately. But what I am trying to tell is that in case of fire, there is a large amount of thermal plume generated by the heat, which drives air also. The airflow is highly dominant, so the smoke tends to propagate
For,
along with air actually in that case.
for here, actually, I agree. I don't have any problem. But
Yes,
when you say the smoke, I have problem because what I feel we need to change in solver up to governing equation also. State equation change is not enough.
of course,
What
of
I
course,
think.
of course. The case that he is trying to show is a fire actually inside a mall. So I think it's perfectly justified to use this gaseous approach in this case.
Okay, so Arun sir, I think we can take the questions later stage. We can
Sure, sure,
continue, I think.
sure.
Okay.
Chandra sir, can you please?
Yeah, that's all I want to share. Uh, so if you have any further questions, we'll go ahead.
So anyone else want to ask some questions? Please, they can raise your hands.
Okay, then we'll stop here. Thanks for everyone joining
Okay,
this
so
session.
thank you for this hands-on training, sir. I hope everyone has enjoyed this hands-on session. Um, Okay, Yadu sir, anything else that we need to
Sir,
add?
we'll be sharing the link for the feedback.
Okay, so the link for the feedback will be shared in the chat box here, as well as in the WhatsApp group. If anything, if any errors are come up, please contact us in the WhatsApp group. Okay. Thank you all, ladies and gentlemen. I hope you found this today's session informative and useful. Thank you for spending this time with us, and kindly join the sessions, tomorrow's session at scheduled time. Thank you, everyone.
Thank you.